Welcome to BKW Physics. I'm Mr. McConley. We're going to do the general interface relationship. Now yesterday we did this relationship, which is called Snell's law. It basically says an index of refraction times the sine of an angle equals an index of refraction sine of an angle. And it's a refraction thing. So when you're changing material, you're going to change speed. And when you change speed, you're going to change direction. You're going to change your angle. That's what this is all about. But I'm going to show today that this can also be set equal to some other things that you already know from previous knowledge. So the first thing I'm going to do is I'm just going to rearrange this. I'm going to say, okay, sine theta 1 over sine theta 2 is equal to n2 over n1. I've just moved around with the n's on one side, but the sine theta is on the other side. But what I want you to recall here, pulling back previous knowledge from yesterday, is that n's were actually, index of refractions were actually the speed of light in a vacuum divided by the speed of light in that material. It was c over v, speed of light in a vacuum over how fast you're going in that material. And if you divide those two, it gives you the n value, because it's a ratio. And the units cancel out. There's no units on n values. Likewise, then n1 would also be c, but it would be over v1, because you're talking about a different material. So if you kind of plug that back in here, what you're going to get is you're going to have the sine theta 1, you're going to have the sine theta 2, you're going to have the n2, you're going to have the n1, and then in this place, you're going to have c over v2, and in this place, you're going to have c over v1. But that's like a complex, messy fraction. And what you can do is the c's can get canceled out. So in the end, you're left with 1 over v2 and 1 over v1, but I don't like those type of fractions, so I'm going to flip it, and I'm going to make it v1 over v2. Did you see how I did that? That makes sense. So actually now you can say the angles are equal to the n values, and they're also equal to how fast you're going. So you have another way to compare or set it equal. But it doesn't stop there. There's more. Velocity, you remember from last chapter, is frequency times wavelength, right? So this one would be 1s, and this one would be 2s. Alright, so fine. Let's write it all out again. Sine theta 1, sine theta 2, n2, n1, v1, v2. Alright, now we got f1 lambda 1, f2 lambda 2. But what do you smart people know about the frequency when you change materials? It remains the same. So this is really not 1 and 2, it's f and f. They're the same thing, they're the same frequency. So what's going to happen to them? So they're going to cancel, gone. I'm actually just going to erase them because they don't need to be there. This right here is what we call the general interface relation. It says that angles can be equal to indexes, can be equal to speeds, can be equal to wavelengths, and now you can combine any of these when you need them. Like you can take these and set it equal to these, or these and set it equal to those. It's a great little equation, and you'll find it in your reference table. Alright, that being said, the other thing we really need to do, and I'm going to ask Wendell, my student, to come up and help me out here, is we need to do a practice Snell's law problem, because we really didn't get to do one of those yesterday. We ran out of time. So I'm going to take a laser pointer, and I'm going to do it with the lights on, because Wendell's going to be able to see from his perspective. It's bright enough, and you can't see it on the video. That's all right. I am going to hold this plastic block right here, and I'm going to shine the laser beam in, and that seems like a good thing there. I'll go ahead, Wendell, and mark a few points so we have some reference there. Perfect. Thank you. I think that should be enough. I might have to call you back if it didn't work out quite right, but let's try it out. So basically we got that light's coming in. Try to be as accurate as possible so we get a decent result here. The light's coming in there. This was the laser beam coming in. Laser beam was going out here. Now obviously you're not going to be able to reproduce this perfectly in your notes, but if you can kind of have a sketch of it, and we'll just label it up properly. And then the light must have gone like this in between. Now, the next thing we need to do is we actually need to draw a normal line here. And I think I'll do normal lines in blue. So, normal lines, there's going to be one right here. And I'll spin it around to try to be accurate here. So there's your 90 both ways. So what I'm trying to do is I'm trying to establish this normal and trying to make sure it's very accurate, or as accurate as I can make it with a whiteboard marker. Okay, so this is your normal line. Now on this picture, where is theta 1? Well, theta 1 is the angle right here, and theta 2 is the angle right there. That shows how much the light's being bent when it enters this plastic material. Do I care about what's going on over here? Actually, I don't, because that's a whole other Snell's Law problem. The only reason I drew this is for completeness sake of the picture, but in terms of calculating the end value for this chunk of plastic, I don't need this stuff over here. All I need is the first two surfaces. Alright, fine. So, I guess what I need is I need to know what these angles are, so I better take a careful measurement of these, and I'm measuring them from the normal line. So from the normal line, I'm getting an angle of 38. So theta 1 is 38 degrees. Theta 2 is 27. Like I said, I'm trying to be accurate, but it's kind of hard with the whiteboard markers because they're like real fat when you're measuring, so I'm just going in the middle of the line. And what is the N1? What is the material I'm starting in? Air. And air's N value is 1. Well, I don't know what this is, and I don't know what the N value is. That's what I'm trying to find. So let's go ahead and jot down our Snell's Law equation, which is N1 sine theta 1 equals N2 sine theta 2. Now at this point right now, there's no point to use the general interface relation because I don't have anything except angles and N values anyway, so the other two don't really help me out, but other problems they would help me out. So let's go ahead and see what we got. We got a 1 here, we got a sine of 38 degrees here, we got, I don't know what that is, that's what I'm trying to find, and we got sine of 27 degrees. So some people with some handy-dandy calculators, can you tell me, what is the N value here?
1.36.
We got a second on that? A 1.36. Great. So the N value of this chunk of plastic material is 1.36. Let's go to the reference tables, and let's see if that is anything that's listed as one of the normal ones, we'll say. So as I flip through the absolute indices of refraction in my reference tables, page 2, I see ethyl alcohol is a 1.36, but this was definitely not that. I see water's a 1.33, which is close, and this was not water. The only one I see that sounds plasticky is lucite. Lucite is a type of plastic, and they list it as a 1.5. Is it possible that I made some incorrect measurements?
Yeah.
Probably. Is it possible that this plastic is not lucite? Probably. So I'm not sure exactly what the deal is. I'm not sure exactly what that material is. I just got it. I bought it from the store, a catalog, and I don't know what it is. It didn't tell me. But if according to our calculations, we're getting the amount of light and how much the light's being bent, it's coming out to be a 1.36, and that's the way you use Snell's Law.